Okay, so we have introduced some important terms, some terminologies in relation to graphs. So we're going to continue from there. And today we are particularly interested in the graph representation and graph traversals. So our topics are going to be the representation and traversal. So if you recall, in the tree traversals, we have introduced some notion of at least depth first sort of traversal in the form of the pre-order, in-order, post-order. They were all depth first traversal. But today you are going to see another kind of traversal, which is breadth first traversal. So for those who are dealing with graph algorithms, mastering and understanding these depth first traversals and breadth first traversals, how deep you understand, that is going to determine how effective you're going to be in solving graph theoretical problems. Because most of the problems boil down to how well you have understood the DFS and the BFS. So please try to understand them as thoroughly as possible. Okay. And if you have any questions, please stop me. I want your understanding to be as mature as possible. So let's first get started with graph representations. Okay, there are two kinds of representations, very common. One is called adjacency matrix. And this is the simplest possible representation of a graph. So let's take an example. So suppose I have a graph with nodes 1, 2, 3, 4, 5, 6. Okay. So I have all these nodes, and then let's say there is an edge going from 1 to 2. Okay. Then there's an edge going from, let's say, 3 to 2. Edge going from 2 to 6, 6 to 4, 5 to 6, and 6 back to 2. Okay, I just drew some random graph, and as you can see, we had introduced before a graph can be directed or a graph can be undirected. So here I just chose a directed graph. So typically the adjacency matrix representation would mean that you come up with a matrix of vertices, so two-dimensional matrix of vertices. So this actually notation is signifying the cardinality. So cardinality means how many vertices are there, right? So V is a set of vertices. If you remember, G equal to V comma E is the standard notation for graphs, where capital V is the set of vertices and capital E is the set of edges that connect the vertices. Okay. So when we put a like absolute value kind of sign here around V, that in the graph theoretical domain, this is essentially cardinality or the number of vertices. So here we are, this is the simplest possible representation that one can have is this adjacency matrix, where you have the V cross V. So here we have 6 vertices. So we can lay down 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. So it's a 6 by 6 matrix here. And we look here. Okay, there is an edge from 1 to 2. Great. So this is going to be true. That means there exists an edge from 1 to 2. Then is there any more edges from 1 to 2? No. So I'm done with 1. Then next my attention goes to 2. So from 2, you have an edge going to 6. So this is true. And then from 3, it goes to 2. So this entry is true. Then from 4, there is nothing. From 5, it goes to 6. So there is an entry here. And from 6, it goes to 2 and 4. So it's going to be true here and true here. So if you had laid down, so this is, I'm showing in the true and false notation, every entry that is left blank, they are essentially false. So either you can see them as 0 and 1, or you can see them as true and false. So it's a two-dimensional matrix of Booleans, where signifying, so Boolean, if it is true, that means there is an edge from this vertex to another vertex. That's all it means. Okay. So very simple notation here. So as you would imagine, in the case of an undirected graph, so this is a directed graph example. In an undirected graph, the representation, the adjacency matrix representation is going to be symmetric. Why? Because you have the entry I comma j is going to be equal to entry j comma I, right? In other words, if I had removed this directionality of the edges, so from 1, with respect to 1, there is an edge going to 2. With respect to 2, there is an edge going to 1, right? So that's why there will be an entry I comma j, whatever it is, whether it is 1 or 0, will be the same as the entry between j and I in the case of undirected graph. So, so one can actually save only the lower diagonal, like one can, because it is symmetric, so one can choose to just have a triangular sort of representation in the case of undirected graph, because of one can exploit that symmetry. So overall, the maximum possible edges in a directed graph. So directed graph, as I also indicated, is also known as digraph. So in a directed graph, the number of possible edges is v square, right? So which is quadratic. So this is clearly quadratic. So you are paying quadratic space overhead. So in the case of undirected graph, the number of edges is v square divided by 2 because of the symmetry. So clearly, it's this quadratic space, so it's a lot of wasted space. It can be a lot of wasted space, a lot of storage overhead. Okay. There are two kinds of graphs I just want to very quickly point out, just definition wise. Planar graphs are those where no edges are crossing. And as a result, there is a linear number of edges as opposed to quadratic. So here, the order will be order of V. And there is another kind of graph called sparse graphs. This has got far fewer edges. So you remember we did one assignment in the beginning of this course where we talked about the sparse matrices, right? Only a few entries are valid. In other words, the graph may have millions of nodes, but maybe out of millions of nodes, only 30 of them are actually having connections. So far fewer edges than what is possible to store. So here there will be, you can imagine, maximum space overhead in the adjacency matrix representation. So therefore, we have to think about another representation, and that is adjacency list. And this is a very common representation, common choice of representation when it comes to graphs. So adjacency list. So this is just a collection of linked list. So every collection of linked lists. So each vertex V has a linked list of edges that are outgoing from V. Okay. So how it would look like, it's a collection of linked lists. So in this case, there will be 6 of them. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So if we just copy paste the same thing. Okay. So that you can see it side by side what we are doing here. So this is our graph. Let me just do it again. Okay, so here we have got 6 entries. 1, 2, 3, 4, 5, and 6. So each of this is a linked list of edges, right? So from here, we are going to, so 1 is connected to 2, and that's it. So 1 is connected to 2. Okay. So 2 is connected to 6. And that's it. Then 3 is connected to 2. Then 4 is connected to nothing. Then therefore we can just ground it. 5 is connected to 6. And then 6 is connected to 2. And 2 is connected to, sorry, 6 is also connected to 4. So it goes through the list of the outgoing edges. So this would be the adjacency list representation. So you can, if you contrast with the adjacency matrix versus this, you can see the main challenge here is the difficulty in lookup. So if you want to ask the question, is there a connection between the pair of vertices? Here it's just a order 1 operation. You just have to look up. But here, in the worst case, it can be order of n operation, because you have to traverse through the entirety of the linked list. So difficult to look up. That's the main overhead here. Okay.
Wait, wouldn't it not be n squared? Because like you have to loop through the um
N squared for what?
it's like, don't you have to first loop through like
No, you're asking the question, is there an edge from 3 to 2? Okay? So you're just looking up from with respect to 3, and you have to traverse this particular linked list. Okay? So it's order of n in the worst case.
Okay.
Okay. So if the vertices are represented by consecutive integers, then you can use an array of lists, right? So your vertices are represented by consecutive integers. You can use an array of lists, right? It's just 1, 2, 3, 4, 5, 6. That's it. And here is where you can think of the application of hash table comes in, right? So what is the hash table application here? So if the vertices have names, right? Like if it's a city graph, right? So names like Boston, right? Suppose that it's just connection between different cities, right? Then you can use a hash table, right? To map the city names, right? The strings. Or for that matter, it can be any object that you can hash. So you can use a hash table to map the strings to the list, right? So here the key would be essentially the name of the vertex, and the value would be the list, right? So adjacency list is clearly more time and space efficient for sparse graphs. So adjacency list is more space and time efficient for a sparse graph. There are only few number of edges, but less efficient for a complete graph. So complete graph would mean that you have edges, every single edge that is possible to have in the graph that is there, right? Every possible edge is there in the graph. Okay, is that clear? Okay, so now we are going to the most important topic for graphs, and that is graph traversals. As I said, please try to understand this graph traversal as thoroughly as possible. So what is the goal of traversal? So just like in tree, it's about visiting, right? So you want to visit, and remember, visiting means performing some operation, correct? So the graph traversals, they visit. So every vertex once, okay? In the case of tree, that question of once does not arise so much because there's only one path from one vertex to another. But in the case of graphs, that question arises. Therefore, here very specifically, graph traversal means visiting every vertex once. And as I was mentioning, there are two ways. One is a depth first search, also known as DFS, and breadth first search, also known as BFS. So this corresponds to the level order traversal in a tree. Like if you apply, because like the tree is just like a kind of graph in one sense. And therefore, if one is applying the breadth first traversal, that will lead to the level order traversal. And depth first search typically is like the pre-order traversal in a tree. Okay. So what does depth first literally means? Depth first, as the name suggests. So you want to go as deeply and as early as possible. So this is signifying as deeply and as early as possible. So I want to visit the node that is reachable from me as soon as possible. Okay.
Can you give an example of that?
We are going to.
Okay.
Okay. So clearly, opposite of depth first, in the case of breadth first, would mean this is going kind of more like level by level, as opposed to going as deeply as possible. So clearly, there are many ways to get from one node to another. In a graph. So because there are many ways, therefore, so let's take an example. That is a good time. Suppose I connect some vertex here. So this is some graph, right? So if I number them 1, 2, 3, 4, 5, 6. So from 1 to 6, if I have to go, you can see that I can go from 1 to 2, 2 to 5, 5 to 6. But I can also go 1 to 2, 2 to 4, 4 to 6. Or I may go 1 to 3. I can come back to 2, go to 4, come back to 3, go to 2, come back to 5, come back to 6. There are many, many ways of getting there, right? But we want to visit only once. That's our traversal. Now, because there are possibilities of visiting the node more than once, therefore, we need to track whether we have visited something or not, right? Therefore, we have to introduce a notion of visited. If you do not do that, if you just apply, keep visiting, then it's very difficult to figure out when to stop. Therefore, every vertex has a Boolean visited. Now one can think of that one may keep the visited flag, the Boolean flag, directly inside the vertex, but that may not be always desirable because you are actually increasing the load of the node because you are adding one extra field. So that has got space over it, and you may or may not need it, right? But typically we need it, so that's why it's a design choice. But one can choose like making it more specific to the context, one may like to map the vertex to the visited. And whenever the question of mapping comes from vertex to visited, you just learned the best way to map is hash table. So if you remember the hash table, like we said that the mapping to the mapping world, or the hash table, when it is mapped into the world of maps, like where you have a relationship established between one type and another. So when you're trying to establish that relationship, so that relationship, what we are also referring to as map, can be an ordered or an unordered relationship. Like in the case of hashing, it's like you're throwing the bunch of entries into the buckets in a very random fashion, right? So you cannot figure out the sequence in which the vertices are inserted in the hash table. So there is no rhyme or reason to the ordering of those entries. And therefore there is a clear choice between ordered map versus unordered map. So hash table is great for searching, but it is not great for sequentializing or maintaining some consistency of the ordering. So if you have to list down the entries from the bucket, it will come out in a totally arbitrary order. But when the question of just finding comes, the inserting and finding, it's a great data structure of choice. So here in this case, we just want to know whether a vertex is visited or not, and therefore hash table can be a great choice. So every vertex has a Boolean visited field. Okay. So that tells whether we have visited the vertex before. Okay. And as I said, there are two ways of thinking about it. One is that you have the visited field inside the vertex, or you can think of having a map or having a hashing going on from the object vertex or object node to a Boolean field, right? So one can think of an unordered map. So this is either or. Either you store that, or you have an unordered map going from a node star, right? This is your vertex, to a Boolean value, which is saying that whether I'm visited or not. These are two different ways of thinking about it. That's all. And here unordered map essentially literally means hash table, where you're hashing this node star, this pointer, into an entry which is storing the Boolean value, right? The value. Okay, so today we just want to discuss the depth first search, how we can utilize this. So depth first from 1. So you wanted an example, right? So from 1, where do I go? So if I start here, I can start visiting from anywhere, just for the sake of beginning the search. I'm choosing 1. I could have chosen 5 also. I could have chosen 4 also, but I just chose 1 as a starting point. So from 1, I can go to 2, I can go to 3, right? Through adjacency list, I will immediately see that 2 and 3 are there in my list of connectivities with respect to this vertex 1. So these are the neighbors of 1, another way of putting it. Either you can say these are neighbors of 1, or you can say these are the immediately reachable nodes with respect to the node 1. So from here, I can go in any direction. I can choose to go to 2, I can choose to go to 3. So let's say I choose to go to, let me not color this, let's just hold on. So let's say I choose to go to 2 from here, okay? Then where do I go when I have to go depth first? So as I said, I want to visit all the nodes that are reachable from me as soon as possible. I want to just go deep Okay. Therefore, I have to leave aside this visiting 3 for now. As soon as I reach 2, I want to reach its neighbors. So I have to make a choice between 4 and 5. Let's say I choose to visit 5. So I will go here. So I visit 5. And then from here, I don't want to come back and then visit 4, but I want to keep visiting, however farther I can go. And that is why it is called depth first. So I go to 6. Okay, now from 6, I do not have anywhere to go. So I come back to 5 to see what else to visit. There's nothing else to visit from 5 either. I come back to 2, and then I see that 5 has already been visited, so I don't want to visit again. So I have to visit something which is unvisited. So I visit 4 here. Now from 4, you can see there is something that there's an edge to 6. But the problem is that the 6 has already been visited, so I don't want to visit it again. So from here, I have to see what other node I can visit. I can see that I can visit 3 here from 4. So I will, from here, I'll visit 3. Okay. Now from 3, there is a connection to 2, but 2 has already been visited, so I don't have to worry about it. So from 3, when nowhere to go, so I will come back to 4. So 4 has been completely visited in the sense that all the children have been explored. So I come back to 2. So again, the children of 2 had been visited. So I come back to 2 now. From 2, I come back to 1. And so from 1, there is nowhere to go because 3 has already been visited. So this I declare that I have completely traversed the entire graph in the depth first search manner. Any question on this? Is the traversal order clear?
So
What
it
would be the
doesn't matter if we choose like 3 or 2.
Yeah. So you tell me, what is the order in which go? Will it choose to visit?
Because like I'm like when you initially choose 2, right? Like we don't know which one will be deeper, so you can't like.
Yeah, you don't know. So you have to arbitrarily choose that. But what is the basis for that arbitrary choice?
It has been visited or not.
No, from 2, yeah, definitely the question comes, I want to only visit those nodes which are unvisited, right?
Mhm.
But which of the, let's say both of them are unvisited. So I have to choose one. How do I choose? How is the ordering getting determined? So if I'm using adjacency list, then from 2, the connectivities are already stored in a particular order, right? The list has been already created. So I will be choosing the visit order of the linked list, correct?
So it'd be 4, for example, if 4 was
If the 4 is coming first in the linked list,
okay.
it could be 5. So it's essentially the linked list order
Mhm.
as far as the adjacency list is concerned. If it's a question of adjacency vertex, adjacency, not vertex. If it's a question of adjacency matrix, then how are we going to figure out from where to go? So here you can see it's a little complex affair in the case of adjacency matrix representation, because I have to go to the entry for 2, right? And I want to see like which ones have the, I mean, not complex affair, but you have to go through every single entry. That's the point, right? With respect to 2 and see which of them are true, right? So you have to visit all of them with respect to 2 and see which of them are true. And so it is going to follow the order in which the nodes had been laid down. So it's going to be typically follow the numbering order, correct?
Yeah.
Yeah. So that's the key difference here. Another person had a question. Okay. So now we are ready to lay down our algorithm. So with this understanding, and as we say that there is a visited notion here. So we have a graph. So this is our class graph, let's say, okay. So in the public method, I have the traversal. So DFS, right? So this is our void function DFS. How do I write the DFS function? So what needs to happen before I go into the DFS? I need to first initialize the visited field for all the nodes to false, right? That means all the nodes to begin with are unvisited, right? And then I will go through every node, right? So I will go through all the nodes in my graph. So for all nodes, let's say n in the graph, what I would do, I will check if n dot visited is false. So if it is not visited, then I want to call the DFS with respect to that node, right? So DFS on n I'm calling, right? This would be the entry point for my DFS algorithm, right? Okay, so now therefore I need to have with respect to the okay, I can write down in the object-oriented manner. Let me not complicate life. Let's just write down simplistically, like where you're passing in the vertex, right? So this is how it would look like. So void DFS with respect to, let's say, node star n, right? So what is the first thing that we should be doing with respect to n? So as I said, like you can land up in the visit or the depth first search with respect to any node, right? This one I showed just as an example. So let's say you start with 1. So the first thing that you want to do is you want to visit that node, correct? So you want to call n visit. And remember from our previous discussion, visit means what? You perform some action. It can be printing, it can be anything, right? So you do whatever you need to do with respect to that node, right? That's why we call the visit with respect to that node. Okay. And we set now the visited, remember, let's say we have the visited field here to false. This is the Boolean value, right? I'm sorry. What did I say? Why should it be false? It should be true. So I just visited it. So this is now true. Okay. And then for each vertex n, sorry, each vertex p, let's say, such that n comma p is an element of edge. Okay. I think I'm writing like combination of C++ and the graph notation here. Okay, so here what I'm saying is that you're visiting every neighbor or every children, either way, every child of n. Okay, so for each vertex p such that n comma p is an edge here, correct? What do? We have to check whether p has been already visited or not. So if p visited, so this visited is a function that's going to return whether it is true or not. So we can just use it as a variable. This is just to kind of keep things simple and keep things consistent. So if p is not visited already, then we want to call recursively the DFS on p. And that's about it. And we are done, because this is the one that is actually recursively just visiting, right? So DFS algorithm, as you can see, is very simple. So now let's see an application of DFS. Okay, before we look into application, what is the complexity of this? So you can see that we are visiting every single vertex and every single edge, right? So the complexity, the running time, is V plus E, the number of vertices plus number of edges, because we are touching upon every single vertex and every single edge. Okay. So now the number of edges, right? The number of edges essentially is significant, because in the case of adjacency list, this can be a small number, right? But in the case of the adjacency matrix representation, what's going to happen is that you can see that when you come to this, in the case of adjacency matrix representation, when you ask this question for every vertex, you're essentially scanning through all the nodes to ask, is this my neighbor, right? So this for loop is actually order of n in the case of adjacency matrix, right? To ask the question whether there is an edge existing, this is an order of n. And as a result of which, in the case of adjacency matrix, this results in the complexity of order of n square or v square. Okay. But in the case of adjacency list, this is v plus e. Now, of course, the number of edges in a complete graph, we know that how many possible number of edges would be there in a graph with n vertices. It's n into n minus 1 divided by 2, right? This is the simple understanding that how many edges would be there typically. So this is actually n square. In other words, the e in the worst case can be v square. But if the number of edges is not in the order of v square, then the complexity of the depth first search remains fairly linear in practice. And that's the key point. Okay, so now let's get down to today's lab assignment. Okay, I just want to get down to lab assignment directly, because we are fairly late, and I want to help you out a little bit and also deepen your understanding of the depth first search. The problem for the lab today is, how do we find cycles in a graph? Okay, so we have just learned depth first algorithm. So how are we going to apply to detect cycle in a directed graph? So I want to pick your brain first. Any thoughts?
Maybe like if you're at a node, instead of trying to visit the node that hasn't been visited, try to visit a node that has been visited.
Okay. Try to visit a node that has been visited. So here we are trying to find out whether there is a cycle or not, right? Detecting a cycle in a directed graph. So what we want to know is so what we want is is there a cycle given a graph? That's what we want to find out. So now what you're saying is, so from a node, I will start visiting and I will start tracking what is visited, what is not visited. And then what do I do?
If something has been visited, you go there and you have a cycle. But if nothing has been visited or none of the
So one idea,
vertices that are adjacent have been visited,
okay,
then you go
Very-
on to the first one in the linked list.
very good. So if a node is already visited, right? We are maintaining the visited flag. So I can easily see that, okay, I'm about to visit an already visited node, right? Then declare a cycle, right? That's what you're saying, correct?
Yes.
Okay. So now let's look at this graph, okay? So you can see here from 2 to 5, then it is visiting 6. So 6 is marked visited, right? And then it will come again and then about to visit 6 again, right? And you say, oh, I have already visited 6. It's a cycle, but we see that this is not a cycle. But this is a great first thought, by the way. It's a great, this is a most common first thought that is given, but it is, you can see that we are still not able to distinguish between a forward visit versus a backward visit, right? Correct. So just simply looking for an already visited node is not going to get us to a solution. Is that point clear?
Yes. And here's just another idea. Maybe
Mhm.
when you go back, you change the visited flag. So when you end up at 6 from 5, you change it to visited. When you go back to 5, you change 6 to not visited. So then when you come from 4, it's not visited.
Then now how would you identify, how would you
Well,
distribute
because
it?
you wouldn't be going back, like you wouldn't have to go backwards if you were making a loop. You would, so
Okay.
you would go like 1, 2, 5, 6, and then you would go back to 5. So you would unmark 6 and back to 2, unmark 5, and then
Okay.
4, 6, and then back to 4, unmark 6, and then to 3, and then 2, and you have a loop.
Okay. So now let's think about this. Okay. These are great thoughts. So suppose I keep doing this and actually my graph does not have any cycle to begin with, okay? And I'm just doing this visited, unvisited thing, right? But note that the only reason I'm visiting a particular node is that because it is unvisited to begin with, correct? So it will be stuck in an infinite loop, is it not? Because I do not have a clear sense of when to visit, when not to visit. When I'm playing with the same visited flag, which is the basis for me to visit a node. Correct?
Yeah.
So that could be a danger. I mean, although this thought was good. Okay, so where do we go from here? So now let's take this depth first search to another level. Okay, there had been some messages on the chat. I just want to make sure. Okay, so Matt had been handling the question. Great. Okay, thanks, Matt, for answering the questions in the background. Okay, so let's now take the depth first search understanding to another level. So note that when we are visiting a particular node, there is something going on. So one is that from 1, when I visited this node 2, right? And then I chose that, okay, now my node is visited. I visited this node. So when I declared that something has been visited, that essentially meant that I was able to do something with that node. And that's the notion that I carried for visited. But if we extend that notion of visiting a little bit further, where I not only want to know that I am visited, but I also want to know when I am done visiting all the reachable nodes from me fully. Now, this point is very significant. So every node, you can think of every node is going through a phase, okay? So initially all nodes begins unvisited. That's the status, okay? The first time when you visit the node, it goes to the visited status, okay? Which means that I'm able to do something with that node, that's all. I'm able to print, I'm able to check its value, I can do so many things. But then I also do more things with respect to that node, and that I'm able to also visit other nodes that are reachable from there. So from 2, I start visiting other nodes that are reachable. So in other words, the journey of visiting 2 is not yet complete, so to speak, until I have also visited all the other nodes that are reachable from that node. Therefore, that notion of visiting can be extended further, that I can actually visit all the nodes that are reachable from that node. And when that happens, I can say that I have completely visited the node. Is this point clear? Okay, so now for the sake of this example, this example did not have a cycle to begin with. Let's introduce a cycle. So let's say did I have the direction in that? Okay, then we had a cycle. Sorry. We had this cycle, right? But I'm just showing that very clearly now. So with respect to 2, what needs to happen for me to detect this as the cycle? So notice here one thing. How do I visit this 6 twice? How do I visit this 6 twice from 2? I go here from 2, I visit 5. Then from 5, I visit 6, correct? Then I have nowhere to go. Then I backtrack, right? And then I again come back through 4, okay? And then I find, can I visit this? This is already visited. So the point is that I'm visiting this 6. So suppose there had been more nodes here, okay? Just to kind of make things more clear. If there had been more nodes here, okay? What is the point when I'm visiting this 6 for the second time? I'm visiting after this whole graph has been already visited. Is it not? But in the case of a cycle, I'm visiting this node, right? And while I'm visiting the nodes that are reachable from 4 to 3, so we are visiting nodes with respect to 2. So from 2 to 4, from 4 to 3, and then from 3 to 2. So I have not yet completely visited to this 2. I'm in the process of visiting all the nodes that are reachable from 2. And in that process, I'm encountering another node which has got a visited status. And that tells me that I have hit a cycle. So cycle is something that you are in the process of visiting. You have not yet completely visited, and you are encountering the node one more time while it is visited. Is that clear? So the difference between visiting this node twice, right, in a cycle versus this node twice, which is not in a cycle, is that I'm reaching this node 6, right, for the second time after I have visited every single node that is conceivably possible to visit from 6. So this had the completely visited status. Correct? And this one had the only visited status when I visited for the second time. Is that point clear? So now you know how to approach this, that we need a little more status than just unvisited and visited. We need the notion of unvisited, visited, and completely visited. And I want you to actually take this depth first search algorithm and turn into, is there a cycle, by adding this extra state which is able to distinguish between visited and completely visited, and then you would be in a position to detect the cycle. That is just one kind of a way to approach this problem. Okay, there are two other ways one can approach this problem.
Wait, sorry, quick clarifying question. Like I wasn't exactly sure the distinction you made in like saying that something's in the process of being visited or like has already been visited. Like, can you clarify that again?
Sure. So as I was saying, that I expanded or extended the notion of visiting to include completely visited, right? Visited just means that I have visited the self, right? Completely visited is that I have not only visited myself, but I have also visited all nodes that are reachable from me. Is that clear?
Yeah, kind of.
So therefore, in the process of visiting, in the sense that you are not yet completely visited, right? You have just got yourself in the visited status, but you have not yet gotten the completely visited status. And that is why there is a scope for finding the cycle. If you have completely visited the cycle, that means there is no scope for you to find the cycle, right? Because the cycle can arise only when you are exploring through the reachable routes, right? And you arrive at your itself just through the reachable nodes. Therefore, it's still in the process of visiting as far as this extended definition of visiting is concerned. Is that clear?
Yeah, kind of, yeah.
Kind of. Are you able to see this distinction between 2 and 6? Visiting this 6 twice versus visiting this 2 twice. We visited this 6 twice, but this twice is after 6 had been completely visited, correct? Anything that is reachable from 6 had been already taken care of. It is through the backtracking that we are getting opportunity to visit 6 one more time, right? It is from 2, I have not explored other routes to visit 6, right? And therefore, I'm visiting 6 for the second time, going through those uncharted territories, or going through unvisited edges. Is that clear?
Wait, so there would be a cycle like in between like 2, 5, 6, and 4, right?
There is no cycle here. 2, 5, 6, 2, 4, 6. The arrows are in this direction.
Oh, right. Okay.
So I'm making this distinction between this 6, which is we are visiting for the second time, right?
Mm-hmm.
Not having a cycle, not being a part of the cycle, versus visiting 2 for the second time, which is part of a cycle. How do you distinguish between these two? So the case of visiting 6 for the second time is when the 6 has been completely visited. But this 2, which is part of the cycle, is when you are still continuing on with visiting those nodes which are reachable from 2. So you are in the process of visiting.
Oh, so it's not, so like for 2, I'm like when I go, or like, how do I say, when I'm still reaching all the possible nodes from 2, I go back to 2 and it's still not completely visited. So
Correct.
like,
Correct.
that's why it's
Correct.
cycle.
Correct.
Okay.
Because the point is that the cycle is a part of your reaching that node from itself. So therefore, you should not be in a position that you have completely visited it, right? If you have completely visited it, then there is no cycle involving that node. Okay, so I hope that is clear.
Is it, question, is it clear, is it make sense to think about it in terms of like, if I start at node 2, have I reached all of the endpoints? before hitting 2 again? Like that 6 is an endpoint, or but yet if I go through 4 and 3, then I'm getting back to 2 without hitting an endpoint.
You
But
may
whether-
not, you may not have visited those endpoints. You may have chosen to visit 4 first instead of 5. Suppose
Okay,
you have gone from 1, right? You visited 2, where you set the visited flag to be true, right? I mean, not visited flag, but it goes into this visited status, right? You didn't visit this 5. You visited 4. Then from 4, you visited 3. You come back to 2, you declare a cycle.
No, but what I'm saying is that I go looking for endpoints. That meaning I could say, all right, I get to 1, I go to 2, and then 2 to 5 to 6, 6, there's nowhere to go. Then I can backtrack and say, that's a closed path.
You
And
may
then
not, my point is that you may not have visited 6 at all.
No, but what I'm saying is, but if I happen to go 2, 4, 3, 2, then I haven't hit an endpoint. I haven't hit there's no stoppage, and I get back to 2, then it's a cycle. Am I thinking about it correctly or no?
So when you say endpoints, right? Let's be very clear about what is the definition of an endpoint. What is the definition of an endpoint? Endpoint means that from that node there is nowhere else to go.
Right.
That's what you mean by endpoint, correct?
Yes.
So my point is that those endpoints are irrelevant as far as the cycle detection is concerned. You may or may not have visited those endpoints. The point is that with respect to 2, when you are visiting, okay, you're visiting whatever nodes you can visit, okay? And why? You say that again?
No. I understand what you're saying. I'm not sure it's contradicting to what I'm saying, but it's okay. I'll figure it out in the implementation.
So can you say that one more time in a different way? I'm just trying to figure out.
What I'm saying is when I get to 2, I
Yeah.
have 2 options.
Correct.
So then I'm going to say, okay, I'm going to pick one of those 2 options.
Sure.
And if I go to 5 and then to 6, then I'm going to say, okay, 2 to 5 is not a cycle. And
Okay.
if I go to 4, if I go from 2 to 4, then I have again 2 options.
Sure.
So then I could say 2, 4, 6 is not a cycle, but okay, what's 2, 4, 3? Is that a cycle? No, because it goes back to 2. Or I could, and at any point I sort of say cycle is true.
Yeah, sure. You can say that.
Okay.
Yeah.
But essentially when I get to 2, I have to explore every path from 2 to determine if any of them are cycles. And if none of them are cycles, then I would put the completely visited flag.
That's right.
Okay.
And that's exactly what happened for 6.
Right.
When it is not a cycle, you will end up visiting everything else that is reachable. But when there is a cycle, you may or may not have visited all the nodes from that node.
So essentially completely visited means if you're getting to 6 from something, there's not gonna be any cycles there.
Exactly.
Okay,
Precisely.
thank you.
Precisely. Any other question on this? Okay, there could be another way you could have approached this problem. There are actually 2 other ways you could have approached this problem, but the second way we will know when we have introduced the breadth first search approach. But using depth first search itself, another way of approaching is by bringing in the notion of start and finish times. So this is another thing one can introduce, the start and finish times. So suppose one starts attributing as one is visiting. So when one visits 1, it is 1. So from 1, one goes to 2. From 2, one goes to 5. From 5, one goes to 6. From 6, there is nowhere to go. So it finishes. It becomes 7. So at the time unit 7, it completes the visiting 6. Okay. So from 6, there was nowhere to go, but so it comes back to 5. From 5, nowhere to go, so it finishes at 8. Okay, comes back to 2. So from 2, it can visit 4. So it goes here. So from 2, the timestamp increases. So from 8, it becomes 9. So it visited 4 at 9. Then it visits 3 at 10. So from 3, all the nodes are already visited, so it can complete this. So at the 11th time it finishes, comes back to 4, 12th time it completes the visiting of the 4. So comes back to 2, and then comes back to 1. So this is 13, comes back to 1, this is 14. So you can come up with some scheme just based on the start and the finish time. So I will leave that as an exercise if you want to try that route, using the start and the finish time to detect whether there is a cycle or not. So anyways, I thought this is an interesting problem for you to try out in your lab. And that's about it. I'm really sorry that I took a lot of time, but I thought that this topic is such that I wanted to have as much clarity as possible. And next week, which is the last week of class, we're going to do 2 things. One is that we are going to go through the breadth first search, and we're going to also look into the shortest path algorithm. And based on that, there will be a lab. And I'm also going to share some practice questions based on whatever topics have been covered. You can look into them, and then we will also try to solve some of them in the class as a final review. So the main topics for the last class would be the breadth first search, shortest path algorithm, and the final review. And finally, there will be a lab, which is going to be based on the shortest path algorithm. And tonight I will release the homework. I have already released the homework. I just have to send a message on the Piazza, and that is on the hash tables. And that's the last homework, which is going to be due on 11th of this month, which is essentially the day of your final exam as well. Okay, so thank you very much.